Hi, welcome back to week 2 of PASCO Academy. This week we're going to be doing 2 labs about motion, Lab 4A and 4B. They're very closely connected, so it makes sense to do them both together. And I'm Mr. Burns, and I'm joined by my colleague, Mr. Plank. And looks like you've brought in some things for a demonstration. Could you explain what you've prepared for us here?
Yes, Mr. Burns, this is a demonstration of how highway patrolmen can measure your speed in a vehicle on the highway from the air. More specifically, you may have seen signs on the side of the highway that say speed patrol by aircraft. For the longest time, I didn't know really what that meant. I thought maybe the planes that flew above us had radar guns of some sort, but it turns out it's much more simple than that, and it's actually going to help us with our lesson today. And so we've got a plane. We've got the aircraft, that's the patrol by aircraft part, and then we've got the car, the automobile right here, driving on the highway. So how this works is the car drives along the highway, and on the side of the highway, you may have never noticed these giant white markers. And what happens is the officers in the plane, as the car drives by a first marker, they'll start a stopwatch. And then they fly together and drive together. And when the car reaches the second marker, they stop the stopwatch. And now, using that time and this distance, they can figure out how fast the car is going. It's just as simple as that. You know how far it's gone, and you know, using that time on your stopwatch, how long it took. You can figure out how fast it's going.
And so that would be the average speed or velocity that they had. So they could have gone faster in the middle as long as they slowed down, but they're not going to see the plane. Chances are this is going to catch them.
Yeah, that's right. So because we know the distance and we know the time, that is a measurement of the average speed or the average velocity of the car as it's traveling along the highway, not the instantaneous velocity.
So this sort of reminds me of a story a friend of mine told me. He was on a trip on the East Coast, and he took part of his trip on something called the Pennsylvania Turnpike, which is a highway, but you pay a toll based on how many miles you drive on it. So when you enter it, they give you a little slip of paper saying where you entered, and it also has a timestamp. And so normally as you exit, you stop and you give them your slip of paper, and they figure out how many miles you went, and then they charge you based on that. But they also look at the time. And so if you exited earlier than you should have been, that means you were speeding. And so they actually know the distance. They look at the time and they figure out your average speed, and they'll hand you a speeding ticket if your average speed was greater than the posted speed limit. And so this is sort of a practical application of our study of motion. If you ever find yourself in a similar situation, you could work out, hey, what's the earliest I could exit? And then if you were not paying attention to your speed and happened to go over it, you could pull over and have a cup of coffee or something until the time has passed.
But that's not recommended.
No, always obey the posted speed limits. So instead of looking at this conceptually, we want to look at this more analytically. So we have some equipment. You saw the smart cart last week. We're mainly using it for sensing motion. And so it's sensing force. And now we're going to use it for sensing motion. In other words, track its position versus time. And it's kind of a black box measuring position.
Oh, red box.
Red box. And so yesterday I took apart an old one. Don't take apart the one in your classroom. Just to sort of see how it was working. And I noticed that on one axle there's this extra wheel. And so I started looking into that. Mr. Plank, I think you know more about this. How is that working?
Yeah, so the wheel, the extra wheel that's there on the cart is actually an optical encoder. And that's a fancy word for a tool that works like a wagon wheel with a flashlight shining through it. And so as you spin the wagon wheel, there's spokes on it. And that flashlight flashes on and off as the spokes go by it. And if I was on one side, I could count how many flashes are happening. And that could help tell us not only how much the wheel has turned, but how fast it's turning as well. And we'll talk about how the smart cart does that more specifically in a second. But that's basically how it works.
So if there were 4 spokes, then the wheel would turn 1/4 of the circumference in the time between flashes.
That's right.
This, how many spokes is on this? There's a lot of little, let's see, I'll count them. 816, actually 816 bright and dark spots. And so there's 408 reflective spots. That'd be like the spokes, and then 408 gaps. And there's a light that shines on it, reflects back, and it can measure those flashes and turn it into a position data. And then the circuitry could also tell us what time it is at each flash.
Right.
And we can make a graph. So let's do that. So we have the red smart card here, and we have a graph of position time. And so let's collect some data. So that's pretty cool. We had it bounce back. The first part, it's at 0 position before I pushed it. And that's the way the smart cart works, is the default is the origin is wherever it started when you clicked collecting data. So this was 0 position. You can change that if you need to. And then you can see when it started moving, there's a little push with that little curve. Then it's pretty straight. And then when it turns around, you can see that where the peak is, and then it starts coming back. What could we learn about the motion from that graph?
Yeah, well, Mr. Burns, you mentioned a couple of good things, important things. The peak here is where that cart bounced off this end. So we could use this data to do what the officers in the plane do as well, right? So this is position time data. The data that those officers in that aircraft that are tracking your speed is also a position and time data, right? So they know you changed position between those markers, and they know the amount of time it took, and they're using that to calculate velocity. Well, that's exactly what we can do with our data here. And we do that using a linear fit, because the slope tells us how much that position is changing with respect to time. And so to turn that on, what we can do is, first thing is select the data that we want to find the slope of, right? And to do that, you just turn that little select tool on there in the toolbar. Now we're ready to select the data. You can click and drag a box and then turn that linear fit on with the button in the toolbar right there. And there's the slope of that data that's in that box.
And so that would be your average velocity, but here, since it's pretty constant, that was the velocity. And then we get about the same number for when it went back, except what would be different about it?
Yeah, so if we want to analyze the data when it was on the way back, we can just take that box that's highlighted the data and just move it over to the data that we want to take a look at. Oops. Just like that. And the data is about the same magnitude, but it's negative, right? So the data on the way this way on the track was positive, and the data on that way was negative.
And so the highway patrolmen are just interested in the speed, but in physics, we also care about its direction. So that is what we mean when we say velocity. We got the speed, the magnitude, how fast it's going, and the direction. Now, we could also get the velocity a different way. We could have the computer do that calculation, getting the slope between every pair of points. And so that'd be hundreds of calculations. We wouldn't want to do it, but the computer can. And then it could build a graph using all those different average velocities and graph them versus time. But since it happens over such a short interval, the change in time between 2 points is very small, we can assume it's the instantaneous velocity. And that's what you do when you look at the speedometer on a car. You look at it, it says 60 miles an hour. That's really your average speed. Your car is calculating it in a similar way. But over such a short interval of time, we just assume, hey, that's my velocity right now. So let's see what the velocity graph would look like with that calculation.
Okay, let me add a graph here on the bottom. Both the position graph on top and this new graph I made have the same x-axis, so everything's lined up in time. And then I'll just put the velocity that was measured in there. And now we've got position and time on the top, and velocity and time on the bottom.
And it makes sense. You can see it moving in the positive direction at first, That's the way I oriented the smart cart. You can see the push where the velocity is not constant, and then it's fairly constant, maybe slowing down a little bit just because of the way the track is. Then it turns around and is negative.
Yeah, so the data on the left side of the velocity graph is above the x-axis, positive, and below on the right side, which is negative.
So we found slope is important, and I bet you getting the slope of that is probably part of understanding motion. What else besides slope might be important for that graph and other ones?
Another thing that we do a lot in physics is we like to look at the area under a curve, right? Sometimes that area under a curve will help us understand more about the thing we're measuring. And you'll find it's really important when you start measuring motion. And so to find the area under this curve, we're simply just trying to figure out how much area on our graph, literally area, surface area on the graph, is captured by the data above and below the x-axis. And so SparkView has a neat tool that'll help you do that. And all you need to do is use this Sigma tool here to turn it on.
So it's the grayed out part.
Yeah, and so you'll see here the grayed out part represents the area under the curve, and there's some area underneath the positive data, and then there's some area underneath the negative data, and the area under the positive data is positive, and the area under the negative area is negative, and so the total area is just the sum of all of that.
And so the negative part, it's really sort of the area above the curve, but people just don't say that. They always say area under the curve. It's really the area between the curve and the x-axis. In this area, we're not talking about, you know, getting square feet to buy carpet or something. This area would be the units of the graph. And so you can figure out the units of the area. It's a multiplication process. So it would be the velocity times the time. And so it comes out to meters. That might be important too.
Yeah, so you'll find that area plays a very important role in some of the things that we're going to do in both of the upcoming labs.
Now, if I just wanted part of the area, could I use that selection tool to get just the area like we did with the slope?
Yeah, and with the selection tool turned on, just like we did in the graph above, you can just click and drag and form a box. And now the area that gets measured here, that area value, is only the area under the data that's highlighted there, that's selected in that box.
So I think we found that slope and area are really important for understanding motion, and we're going to see both of those used as we do the labs today. And so we're going to get set up to measure the data for lab 4A, and we'll see you in a minute. Okay, we're back and ready to collect data for 4A. Things look a little different. Could you explain what we have set up for collecting data in 4A?
Yeah, this is an inclined track. It's just slightly inclined. And what we're going to do is place the smart cart at the inclined end of the track and release it to roll freely with nothing touching it down the track until it hits the bottom. And we're going to record data during that time and do some analysis of the cart's motion. Before we do that, it's important that we discuss reference frames. And so the reference frame that we choose is always the one that's going to be most beneficial for us in our application. And in this case, it's going to be most beneficial for us to just use the reference frame that the smart cart already uses on its own. Some of the measurements that the smart cart makes are positive and some of them are negative. And that positive and negative measurement is dependent on the direction the cart's moving. And we can tell using this little diagram on the top of the cart here which directions are positive and which directions are negative. And so the diagram is indicating that the X direction this way is positive. So positive X direction is going to be to your left as you watch this video, and negative is going to be to your right. So if the cart is moving in that direction, it's going to be negative, and if it's moving in this direction, it's going to be positive.
And that's different than you're probably used to. You're probably used to seeing on at least a printed page, they make positive to your right. It's okay to make positive to the left as long as we're clear about the coordinate system we're using. And so in this case, to your left, positive.
Okay.
So I think we're all ready to collect data.
Okay, so I'll just go ahead and click start. You can release the cart.
I can see you clicking start. I'll just let go right after.
Ready?
Yeah.
I'll just stop right there. And so we've got velocity and acceleration data, velocity versus time and acceleration versus time. And both of these graphs are on the same x-axis. So everything's lined up in time. And so we can use this data to help find out how fast the car was going, as well as what the cart's acceleration was. And we can also use tools in the software to help determine specific values. More specifically, for a specific value, if we wanted to know what the cart's velocity data was at a certain point, we can simply select the data and then use this tool right here. It's called the coordinates tool. And if we turn that tool on, it puts a little box around the data points, and we can move this tool. We can click and drag and move this tool around, and it'll jump to a data point and it'll tell us the value of any data point that it's on, right? And so if we wanted to know what the velocity of the cart was at 0.950 seconds, we can move that tool there and it'll tell us that value. The tool also can tell us the change between two data points. And that's what this little triangle button is right here. This is the delta tool. And now I've got two boxes, and I can stretch these boxes around, and it can tell me things like the change in the y-axis variable, which is velocity in this case, and the change in the x-axis variable, which is time in this case. So we know the change in velocity, and we know the change in time between those two data points using that tool.
So that'll help you when you're doing your own analysis of this data. And so I have increased the incline of the track, added another book, and I think we just collect the same thing here.
Okay, let me go ahead. Are you ready?
Yep.
So we'll start. Okay.
And for this last one, we're going to put it back to the original incline. And I still have the smart cart, so positive is down the track to your left. But I'm going to give the cart a push up the track, a real quick one, and then just let it roll on its own after that. And so we'll collect data for it rolling up, hopefully not hitting the end, and then rolling back. So it's all rolling freely after I'm done pushing. So you ready?
Ready.
Perfect.
Perfect. And so you'll notice Mr. Burns said, I'm going to give this cart a quick push here at the bottom, and we only care about the time or the data where the cart was moving freely all on its own. And that goes for all three of these runs of data. So there was a point in time where Dan was pushing, but then the cart rolled freely. We're going to ignore all that data where Dan was pushing.
So where's that on the graph there?
And you'll see here on the graph that there is this curved area in our velocity data and this big bump in our acceleration data. That represents the data where Dan was pushing. His hand was touching the cart and pushing it. So we're going to ignore that. And then we're also going to ignore on the end here, there's a little curve down. That's when the data, that represents the data when the cart came back and hit the end of the track again. And then the same thing for the other runs. And if we wanted to see all three of the runs at the same time in our graphs, you can simply just turn on these check boxes here in the legend, and all three runs of data will show up. And so you can see them and compare them if you want.
Very colorful. So the push part looks pretty interesting. Sometimes in physics, we call that an impulse, and that's something we'll study later. But right now, we just want the part where the motion is very uniform, where the lines are pretty straight. So you have the data now to do Lab 4A. So the SparkView file has the data that you're seeing here on the screen, and the student lab handout tells you how to go about doing the analysis and answering the questions. And so you should go and do that and complete that before going on to 4B, which is what we're going to do next. Okay, we're back to collect data for Lab 4B. And at first glance, it looks like the track is set up the same way as it was for 4A. And there's just one change. The smart cart now has been turned around. And so the coordinate system on it, if you're looking at it, you can see positive X is uphill or up the ramp now. And so it is to your right. And so the positive is going up the ramp there. So in this activity, we're going to be using the plunger or the spring-loaded plunger. And so if I put it in there, there's a little trigger button which pops it out. And there are several click stops. First one doesn't come out too much. Second one, third, and then if you really want to use it, all the way in that we saw before. But in this activity, we're going to use the second one. So it turns out it's about just what we want. So we put it in 1, 2, and we're going to use that spring energy, the energy stored in the spring, to launch the smart card up. It's not going to quite hit the end stop, hopefully, and we'll collect the data for it just going up. Right. And I'll stop it.
And we're going to collect position and velocity time data as the cart goes up the track. And we're going to stop recording data just as it stops at the top and starts to roll back down. So I'll start recording data. I'll launch the cart, and Mr. Burns, you grab it at the top, and I'll try to stop it right when you grab it.
Okay.
Okay, so let me go ahead. Start recording data. Launch. Stop. Perfect. Yeah, and so we've got our data, and it includes when the cart was launched, as it rolled up the track, to the point at just where it stopped before it wanted to start rolling back down the track.
And so that's the first run. The second one, I have the click stop into the same position, except I'm not going to catch it this time. We're going to let it bounce back and forth. How many times do you think it'll bounce before it stops?
So let's see. Rolls up the track, turns around, comes back. Well, it doesn't turn around. It just starts rolling back down the track. I don't know. 4 times?
4 times. I'm going to say 7. That's my lucky number. And I'll bet you lunch on it.
Okay, deal.
Okay.
So I'll start recording data. I'll launch. We've got the plunger pushed in 2 clicks. So it's going to have the same amount of launch in this one as we had in the first one. So I'm going to start, launch.
Yeah, it went about the same distance.
Yep.
One bounce. 2, 3, 4, 5. Oh, you're closer, you win.
Okay, I like lunch.
So this last run, we're not going to use the plunger. I'm going to push it with my hand the whole time. And so this is not uniform motion. And I'm just going to move it back and forth randomly for a few seconds and then just stop it at some point.
Just let me know when you're ready.
Okay, whenever you're ready, go.
Okay.
Go up, halfway, back, all the way. Just kind of move it around. Slow and fast. And I'm going to stop it. Oh, right there for some reason.
Perfect.
So now you have the data for the lab, and you should have the skills to do the analysis. What is the main skill they're going to need here on the analysis tools?
This in 4B, you'll be using the area under the curve to do some of your analysis, which we already showed you, as well as using the coordinates tool to find specific values of data points. So you'll use both those tools. We've showed you how to use them. And so the rest of the analysis is left up to you. So we've provided you with the data sets for 2 different labs, Lab 4A and Lab 4B. They are 2 separate handouts, and the data will be provided in 2 separate SparkView files as well.
And so if you're working on Lab 4A, there's a lot of help in the book on pages 110 through 112. Those are the pages that are in the Essential Physics book right before Lab 4A. And so in general, you're going to find that's true. If you get stuck on a lab, go to the book, look at the pages right before the lab, and chances are you'll find what you're looking for. For Lab 4B, the pages are 114 and 115. And so if you haven't already read those, you definitely should. And if you're having trouble with Lab 4B, go back and look at those, especially the figures, and you'll find a lot of help. And so now it's your turn to do the work and finish these labs. We're going to come back in another video and discuss them. And so again, really important that you do all of the labs or as much as you can before you go and watch the video where we go over them. And if you do get stuck, get help from your teacher, if it's allowed, from your peers, and also your book. And so remember those page numbers, consult that, and get as much of it done as you can. We'll see you for the lab analysis video.